session. Lunch will be served in the room just adjacent to this one, so just turn to your right, and the buffet will be set up right in front of the room for you.
Okay, I want to talk about some work that our group has been doing for several years now on the catalytic dehydrogenation of alkanes. My co-authors are Wing-Ken Shen, Naresh Shah, Kathy Shi, Frank Huggins, and work increases to the left on this slide. As Bushy mentioned, we're part of the Consortium for Fossil Fuel Science. That's a UK research center that includes participants from 4 other universities, West Virginia, Pitt, Utah, and Auburn. Let's see, the next slide is that.
That one, yeah.
Well, of course, most hydrogen is produced by from natural gas by a multi-step process, steam reforming, water gas shift, PSA, etc. That does produce significant amounts of carbon dioxide. Catalytic dehydrogenation of gaseous alkanes using bimetallic iron-based alloys, the secondary element is nickel, moly, or palladium, on one of 2 supports, produces pure hydrogen with no CO, which poisons fuel cell catalyst or carbon dioxide in one step. Reaction is very simple, and carbon is produced in the form of carbon nanotubes. This shows the hydrogen production from catalytic dehydrogenation of methane. The balance of the gas is methane. That's all that's produced, hydrogen and methane. And we're looking at it for 3 different catalysts: iron palladium, iron moly, and iron nickel. Catalyst loading is about 5%, and the iron to secondary element is about 70 to 30. As you can see, we've got a pretty big catalytic effect, about 450 to 500 degrees decrease in the decomposition temperature of methane from the thermal case. And in the most active region, from about 650 up to about 800 degrees C, we're producing about 70 to 85% hydrogen in our simple plug flow reactor. This shows catalytic dehydrogenation of ethane. In this case, we were using the iron palladium catalyst. They're all comparable in their activities. In this case, you of course start out by first producing both hydrogen and methane, and then the methane peaks. By the time you get over here, you're really just about back to catalytic reforming of methane, and so the result for the plateau region is very similar in terms of the production of hydrogen. Carbon is all produced in the form of nanotubes. If you're in the more active hydrogen production region above 600 C, the nanotubes all turned out to be multi-wall nanotubes, and this shows the parallel walls of one of the multi-wall nanotubes produced. And if you drop down below 500 C, then you find that you're producing stacked cone nanotubes, and you can see the cone-like structure here, those nanotubes. In terms of time on stream behavior, here we show propane and 2 of the catalysts. The results are pretty active for propane, ethane, and methane. The decrease in activity is about 3% per hour per gram of catalyst. And just for comparison, we showed one with just the iron catalyst, just iron on aluminum, rather than the alloys. And you can see that that decreases in activity about 10 times faster. To determine the active phase, we like to use Mossbar spectroscopy and an XF spectroscopy. And it is indeed an iron nickel carbon austenitic alloy. It is a face-centered alloy that contains carbon. And We also see a significant amount of a secondary phase called personite, which is an iron aluminate. And for catalysts prepared by incipient wetness, which all of these were, we find that the particle sizes are about 20 to 50 nanometers in size on average, and you can see them scattered all around on the aluminum support. And particles, in fact, turn out to be bound to this support very strongly by that personite phase. Well, to get on, most of this work was done several years ago. To get on some of the new work that we've been doing, one of the things that we found, of course, is that the carbon nanotubes are very hard to clean because of the limited solubility of the aluminum support. And I guess we could have used hydrochloric, but we were scared, so we didn't use that. Instead, we went to another more basic type of support. This was a magnesia aluminum oxide support. In which the magnesia to aluminum ratio is about 5, and it's formed by calcination of the hydrotalcite compound. This is very easily dissolved in dilute nitric acid, which greatly simplifies the cleaning of the carbon nanotubes. To test this, we focused on our iron-nickel alloy catalyst, since that's the cheapest catalyst that we have. And these were prepared, in this case, we wanted to look at a more uniform nanoparticle size, and so we went to a surfactant inclusion technique. This illustrates how these were prepared. We followed methods, there are a number of methods like this in the literature. We followed principally some methods that were outlined by Heon, whose group is in South Korea, and then there's another group headed by Sun at IBM that uses similar techniques. Reactive metal salt with the sodium oleate to form an oleate complex. And you make this up so that the iron to nickel ratio is about what you want to get the right alloy phase, to get into that austenitic alloy phase that is most active. And then at a temperature of up above 200 C, particles are nucleated, and then they grow in a uniform fashion depending on the higher temperature that you set. In this case, the results for iron nickel nanoparticles, these are all in the oxide form in the as form condition. They're all pretty uniform, and you can see from this particle size distribution that they're clustered very tightly around 9 nanometers. It's almost 9 nanometers plus or minus 1 nanometer in size. So to prepare the catalyst, we take the magnesia alumina support, and those particles actually are pretty small too. They're in the 20 to 40 nanometer range. And if you do it by incipient wetness, of course, again, a range of particle sizes. If you disperse your nanoparticles in hexane, you can use sonication and drying to produce a fairly uniform dispersion of the iron nickel nanoparticles on the magnesia support. Here are some TEM micrographs. The dark spots, of course, are the catalyst particles, and the light gray particles are the magnesia alumina support conglomerate. You can see the catalyst particles stand out a little better in the stem image. Obviously, we don't have all single particles. We've got some conglomerates of particles that are larger. But we also look at the X-ray maps, and we can see very clearly that we are getting excellent mixing of the iron and the nickel. This is after reduction at 600 degrees C hydrogen. And here are some results for methane dehydrogenation. The iron nickel nanoparticles on magnesia alumina on the left, and iron nickel prepared by incipient wetness on magnesia alumina on the right. And at the 3 temperatures indicated here, you can see the nanoparticles are considerably more active for all of the temperatures where they are active. And to look at the stability of the catalyst, we looked at a little bit larger size catalyst, a half a gram, and deactivation rate is about 0.7% per hour per gram of catalyst. That compares to the earlier rates that I quoted, which were about 3% per hour. Deactivation, you can see it starts slowly deactivating after about 12 hours and gets down to thermal levels at about 30 hours. Appears to occur primarily because the catalyst particles are doing tip growth here, and they're getting embedded inside of the nanotubes, and when they get surrounded, gas no longer gets to them, and that apparently is the deactivation mechanism. You can see a catalyst particle encapsulated in a tip up here. It's elongated. I'm not exactly sure why that happens, but I'm sure there's a good explanation for it. Maybe some nanoparticle nanotube person here can tell me about. But that's the deactivation mechanism. And these are some micrographs of the cleaned nanotubes. These were produced in a more active region, and so they're all multi-wall nanotubes with parallel walls. And TGA indicates that the purity of this particular sample is about 99.6%. So that's a pretty good result. And this is done just in dilute nitric acid, which is fairly easy in the cleaning process. Again, we like to use Mossbauer and Exebs to indicate what the phases are, and indeed the primary active phase still appears to be the austenitic iron nickel carbon, and you can see this from really from the positions of the near neighbor shell peaks in these radio distribution functions that are produced from the XF spectra. The dashed line here may be due to the carbon. You have to do a pretty serious analysis to prove that. I believe that Lin Shin has done some of this analysis, and she has a poster over here, and she'd be happy to talk to you about that. Well, if you decide you want to use this method and you're making 1 million tons a year of hydrogen, of course you won't make any CO2, which is a good thing, we're told. You're going to make a lot of nanotubes, and you might well want to ask the question, what do you do with all those carbon nanotubes? Well, we all know there are lots of applications, but this would be pretty high volume if you start to get into the quantities of hydrogen that you really require for most of the things it's used for. There are some uses that could be pretty high volume. There's a lot of interest in high-strength materials. Polymers reinforced with nanotubes, composite materials, and so forth. People are interested in energy storage, supercapacitors, and there's been a lot of work on hydrogen storage. Most of it has not really been too successful lately, but certainly these would all be potentially high volume uses. Some other uses that maybe aren't such high volume, but might be of some interest to us, are as catalyst supports. And of course, there are lots of electronic applications. And in the end, if you decide that you can't use it all, it's a lot easier, I maintain, to store carbon than it is to store carbon dioxide. So perhaps you can just hang on to it for 50 or 60 years until we run out of carbon, and high purity carbon source might be pretty valuable at that time. We've been looking a little bit at nanotubes for catalyst supports and also possibly for hydrogen storage. These are some materials that were prepared with approximately 5 nanometer palladium using the same surfactant inclusion method that I mentioned, deposited on some of our stacked cone nanotubes, and you can see the wall of the graphene sheets coming out at an angle from the surface of the nanotube over here. Haven't tried any hydrogen storage work yet. Really looking for a collaborator to do some of that work, as a matter of fact. But we have done a little bit of catalysis work, and one one thing that might be of interest is producing hydrogen using these sorts of catalysts. So we put some platinum nanoparticles onto stacked on nanotubes, and at a little over 300 degrees C, you can decompose a lot of cycloalkanes and produce pure hydrogen and aromatics. Cyclohexane is the most obvious one. It decomposes to hydrogen and benzene, and then you get similar results for tetralin, methyl cyclohexane, and decalin. You can see that you get complete decomposition, getting 75% hydrogen volume percent, so that's the right amount for total conversion. And you get this with 1% or 1/4% of platinum. You drop down to 1/10%, it does decrease slightly. So, to summarize, catalytic dehydrogenation of alkanes is a one-step method to produce pure hydrogen with no CO to poison your fuel cell catalyst or no CO2 to produce global warming. Carbon is converted to nanotubes. You can control the form of the nanotubes by varying the temperature of the dehydrogenation reaction. And the catalysts are very cheap. They're iron-based. The iron nickel one particularly is cheap. Iron moly isn't too expensive. Iron palladium is interesting. Maybe you wouldn't want to use that. The magnesia alumina support looks preferable if you want to use the carbon nanotubes as a valuable byproduct, because it's very easy to dissolve and it makes it very easy to clean those nanotubes to impurities of greater than about 99.5%. Nanoparticles work better. They seem to be better by a factor of at least 3 or 4 in terms of the stability and activity compared with catalysts prepared by incipient wetness. And finally, we can also dehydrogenate liquids. Platinum nanoparticles on the stacked on nanotubes has great activity for that. So if you ever have a fuel cells car and you want to make your hydrogen on board, this would probably be a much better way to do it than onboard reforming. And of course, we want to acknowledge our support from the Department of Energy and the Office of Fossil Energy, and particularly our friends at the National Energy Technology Laboratory. And thank you for listening.
The floor is open for questions.
Did you test the nanotubes for strength? I mean, how
I'm
would
sorry?
those be, your nanotubes
Yeah.
that you're producing? Have you tested those for strength? How would those compare to some of the other traditional methods of making?
Well, nanotubes have huge tensile strength, and that's the reason that people are interested in trying to incorporate these into polymers and into various composites to increase the strength. One interesting thing that somebody was talking about was a space elevator using nanotubes to support the elevator that takes you up to the satellite. I'm not sure how practical that is actually, but in terms of strength, they are very strong.
Any other questions? If not, please help me thank Jerry one more time.